Hi Rizwan, thank you for your question. I hope you're enjoying half term. The question was from exercise 7F and it was part B of question 8. I'm going to go through it on the board here and talk you through the ideas involved. The first thing that we note is that the geometric sequence's terms are defined in the following way. Now that is different from the normal definition of a geometric series. We've got this constant at the end here. Normally we've just got a coefficient, a base and an index. And as a result, this is not in fact a geometric sequence at all. And let's look at why we know that. The first thing that we can do is we can get the first three terms. That was part A, so you should already have this. U1 is given as 1 when you've calculated it. U2 is given as 1/3. And U3 is given as minus 1/9. To get a common ratio, we can divide subsequent terms. U2 divided by U1, well, anything divided by 1 is itself. So from here, we would say that we might think that the common ratio equals 1/3. But then if we check here, minus 1/9 divided by 1/3 is the same as minus 1/9 times by 1/3, which would give us a common ratio of minus 1/3. Well, that's not a common ratio at all. So this is not a geometric sequence. However, there is a technique that we can apply to find out the sum. And it goes back to something that we did when we were looking at the initial proof of the equation for the sum of a geometric series. I'm going to show you that now and then relate it to this question. I've lost my board rubber. That's no good. I found my board rubber, just like a real lesson. So in a geometric sequence, if we want to know the sum, well, the sum to n is going to be equal to the first term plus the second term plus the third term and so on until the nth term. Now we know that this is given using a formula. We can say that the sequence is equal to the first term plus the second term, which is plus the third term, all the way up to the last term, which is given by n minus 1. Because if you remember, the first term is being times by the common ratio to the power 0. So 1 minus 1 gives us 0 for the first term, n being 1, 1 take away 1 gives us 0. Here in the second term, we've got the common ratio to the power of 1. There is no power, so that's the power of 1. And the second term, n is 2 minus 1 gives us the power of 1. In the third term, we've got n is 3 minus 1 gives us the power of 2. In the final, the nth term, n take away 1 for the same pattern gives us n minus 1. Okay, so that's our sequence there. Now what we can do is a little trick where we times everything by r. So the sum is being times by r, meaning that this term here, a, is being times by r. So that would give us AR. Now I'm going to write that here underneath the matching term here, but this is the one that it came from, so I kind of moved it across. If I take this term and times it by r, the r is now squared, and you can see perhaps why I'm offsetting them so they align with the equal terms above. This term here, if I multiply it by r, gives me AR to the n. Because I'm increasing the number of r's by 1. There are n minus 1 r's. One more is n. So I've got AR to the n. However, the previous term, which would have been AR to the n minus 2, now becomes AR to the n minus 1. Now here's the clever bit, we subtract them. RSN minus SN. This minus this. Well, these all cancel out. And any terms in between would as well. I'm left with the AR to the power of n minus the a. Now, what I'm going to do is I'm going to tidy this up and we're going to get the equation. This isn't for this question, but the method's very similar to the method we'll use in this question, and this is a standard technique. So I thought I'd show you the standard technique, because it might, well, as it applies to this question, it may apply to others. But it's worth it. This is a hard question. This would be your sorting out the A's from the B's type students. So, in this question here, I'm going to pull out Sn as a common factor, leaving R minus 1 inside the brackets. Over here, I'm going to pull out A as a common factor. Okay, now I'm going to divide through by R minus 1. And put that on the bottom there. Some people might say, why isn't A being divided by R minus 1? Well, A is being times by this, therefore the product of those being divided, you don't have to divide them both, because they are together, effectively. It's not like a series of terms being added together, a common arithmetic or algebraic mistake. This is the formula that we get for the sum, and we've used the first principles method to sort of show where that came from. I'm going to use that method on the tricky sequence that we've got to find out what the sum of the series is. Okay, so I'm going to clear this off, pause if we have a look at it. And I've got a better pen. Also, if I could be bothered, I would have edited out that bit where I was wiping the board, but you know, you can just fast forward because it's my holiday. I'm doing enough work already. Okay, so where were we? We had the sum to 15, and we needed to show a particular value. We needed to show that value, which was going to be minus 9.014 to 14 figures. We'll get there in the end, but let's start off at the beginning. We are finding the sum to the 15th term. If any of you were unsure about that sigma notation, that's what it means, S15. Just another way of writing it. And what we're going to do is we're going to take the expression they've given us for each term. Now, the expression for a term was given as 3 brackets 2/3 to the n minus 1. However, I'm going to use the same method as last time. I'm going to be specific in my n's. This is the first term. So n is 1. It's worth noting here, in this example, they haven't got that n minus 1 trick that we saw, where the first term didn't have a power of 1, it had a power of 0. The second term had a power of 2, no, had a power of 1. They all came down 1, with the last term not having a power of n, but having a power of n minus 1. The rule given in the question does not have that minus 1 part in it, so we have to work within what they've given us. So the power is 1 for the first term, not 0 by subtracting 1. Okay, I'm going to put that in square brackets because the second term is coming next. Now the second term, we've got 3 brackets 2/3 close brackets to the power 2 minus 1. Okay, that's our second term. In the same way, I've just substituted in 2 in the place of n. And I could carry on, but I'm going to jump ahead to the final term, which is going to be 3 2/3 power 15 minus 1. First, second, blah, 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 15th term. Okay, That is the sum that we've got. Now we could work out every single value and add them all up, but that's not clever maths, that's just arithmetic. So what we're going to do is we're going to do the trick that we used to get the formula in the last bit I showed you. So what I'm going to do is I'm going to take this and I'm going to times it by r, but we know sort of what r is. Well, we don't have an r, but we have got this 2/3, which is sort of in the place of it. So I'm going to have a little play with that. But before I do, I want to deal with these minus ones. There are 15 terms, so there are 15 minus 1s. Rather than take 1 off each of the 15 terms, I'm going to rewrite this with 15 taken off at the end. This term here is that term, but without 1 taken off. This is this term, but without the 1 taken off. This is the final term, but without the 1 taken off. There were 15 terms. I've taken off those 15 ones all in one go at the end. And this is still the sum to 15. Now this is the bit that I'm going to play with. What I'm going to do is, this looks a lot more like what we're used to. We haven't got that constant being taken off at the end. Admittedly, the powers are all 1 higher than we're used to, but in the place of where the common ratio would be, we've got the 2/3. So I'm going to use that. What's 2/3 of s to the power 15? Well, it's s to the power 15 times by 2/3. I'm going to take each of these terms and times them by 2/3. 2/3 to the power 1 times by 2/3 is 2/3 to the power 2. The power increases by 1. Over here, I've got 2/3 to the power 2. Another 2/3 in there increases the power to 3. And we'll carry that on, but we're not going to. We're just going to put dot, 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 giving us the final term in the sequence of 16. Now, it's important to note that as these are a series of terms separated by addition or subtraction, when multiplying by 2/3 we have to multiply every term, including that 15, and 2/3 of 15 is 10. 2/3 of minus 15 is minus 10. Okay, so now we've got the 2/3 going on there. Now what I'm going to do is I'm going to subtract. I'm going to start with the sum, and I'm going to subtract 2/3 of the sum, which will end up giving me 1/3 of the sum, right? The whole, take away 2/3, leaves 1/3 left. And I'm going to do some subtraction here as well. Now you'll notice if I do this take away this, these two cancel. And in fact this one would cancel as well. And there'll be one for that one to cancel with too. We'd only be left with the first term of this one and the last term of that one. So I would have 3 2/3 to the 1, and I'm subtracting that. Even though it's a positive term, remember I'm subtracting 2/3, so I'm subtracting this, so that's coming off negative. Now I'm left with minus 15 take away minus 10, which is the same as minus 15 plus 10, which is minus 5. And as you can see, this is starting to boil down. It's a lot more fun than calculating 15 terms and adding them all up and worrying about rounding errors and stuff like that. What I'm going to do now is I've got 1/3 of the sum, is I'm going to just times everything by 3, giving me the sum to 15. If I times everything by 3, I get 9, and I've got 2/3 to the 1, minus 9, 2/3 to the 16, minus 15. Now, down here, 9 times 2/3 is going to give me 6. So that's 6. But I'm minusing 15. The result of that is minus 9. And I've still got the minus 9 times 2/3 to the 16. At this point, if you plug that in your calculator, you get the required answer. Done.